In this problem, we're going to investigate a whole bunch of statements and determine if these statements are true or false statements. We've worked problems like this before. The difference with these statements is they involve the quantifiers that we've been investigating, things like for all and there exist. So here in part A, let's look at this statement. For all x, there exists a y such that x minus y equals 0. And the question we need to answer is this a true or false statement? Well, obviously this is a true statement, and that's easy to think about. For any x that you want to pick from the natural numbers, whether that's 0, 1, 2, 3, 4, let's just say x is 4, is there a value y? Does there exist a y also in the natural numbers such that their difference is 0? And there obviously does. When x is 4, I can choose y equal to 4, which is in the natural numbers, and then 4 minus 4 equals 0. And then I can do that no matter what value of x is picked. So for all x, I would choose y equal to x, and this statement would always be true. So that was pretty easy. Let's look at another one. For all x, there exists a y such that 3x minus y equals 0. Is this a true or false statement? Well, no matter what x is picked out of the natural numbers, 1, 2, 3, 4, 5, 0, whatever, 3 times that is just another natural number. So again, let's pick a concrete example to make this concrete. Let's let x equals 7. Well then, 3 times 7 is 21, and I would just choose y to be 21. So there would exist a y such that 21 minus 21 is equal to 0. So this is always going to be true, and it's true because I would always just pick 3 times x for my value for y to show that there exists a value for y. So this is a true statement. Part C, let's change it just a touch. What about for all x there exists a y such that x minus 3y equals 0? We might be tempted to call this one true again, but it's slightly different than what we did in part B. Let's think about the case when x equals 3. When x equals 3, I need to come up with a y such that 3 minus 3y is equal to 0. Well, that's easy to do. Y would equal 1, and I would have 0 equals 0, and this would be true. But what about when x equals 1? I need 1 minus 3y to equal 0. The only way that can happen is if y is equal to a third. And y equal to a third is not a natural number. Okay, so there are definitely cases where the value for y that I need is not a natural number. So this is a false statement. This is not true. And there's a specific example, just consider the case x equals 1 that we just talked about. So when establishing a statement is false, all you need to do is find one spot where it fails to be true. So here's our counterexample right here, x equals 1, that tells us this is not a true statement, it is false. Because in that case, y would have to be equal to a third, which is not in the natural numbers. Okay, let's look at another one. D. There exists an x and there exists a y such that x plus y equals 15. So this is an existence proof. We just need to come up with one value for x and one value for y to make this statement x plus y equal 15. Is this true or false? Well, obviously this is true. And it's true in lots of different ways. There's actually a whole bunch of ways I can come up with this. X equals 5 and y equals 10, those are both natural numbers, and they sum up to 15. So there's one example I can give you that makes this a true statement, because I've proven that there exists an x and there exists a y with this property. I could just have easily have picked x equals 8 and y equals 7. That would have been fine too. So showing that there exists an x and there exists a y is very easy for part D. What about part E? For all x, x greater than 5 implies that for all y such that y is greater than x, that y is greater than 5. So this is a much more complicated expression. You got to kind of break it down into its parts. The statement is that for any x in the natural numbers that I pick that's greater than 5, so this would include the numbers 6, 7, 8, 9, 10, 11, etc. This implies that for all y such that y is greater than x, so since x was greater than 5, x includes 6, 7, 8, 9, so y greater than x means y has to be numbers like 7, 8, 9, 10. This implies that y is greater than 5. Well, obviously this is true for the numbers we just listed. We said that y has to be 7, 8, 9, 10, 11, and up. So clearly y is greater than 5. So this is a true statement. Let's do something similar. What about for all x greater than 5 implies that for all y such that y is greater than x, that y is greater than 7. Is this true or false? Well, just a minute ago we said x greater than 5 includes 6, 7, 8, 9, etc., which means that y has to be 7, 8, 9, 10, 11, etc. So the number 7 is included in the values for y here. Is 7 greater than 7? Well, that's not true. That's false. 7 is not greater than 7. So this statement is false. It is a false statement. If I had changed this problem just oh so slightly and made that a y greater than or equal to 7, then this statement would have transformed into a true statement, because we know that y is either 7 or 8 or 9 or 10 or 11 or 12, and y is greater than or equal to 7 in each of those cases. I could have transformed this into a true statement. So this kind of just emphasizes the fact that when working with natural numbers, you kind of need to be careful with inequalities and whether they're strictly greater than, something like this, or greater than or equal to. That can have a big impact on whether your final statement is true or false.